Okay, this is section 14.2. We are going to still be solving systems of equations. However, we're going to do three-dimensional equations and three unknowns. So three variables, three equations. Again, a solution is a point that satisfies all three equations. So this is how this works graphically, and you don't have to know this, but just for your own benefit. When you have a line in three variables, it's actually a three-dimensional line, which is a plane. It's a plane. And so each one of these equations down here with three variables is an equation of a plane. And so how can three different planes intersect? Well, in this first example here, we see them intersecting in one point. In this second example, you can see that they intersect in a line. That's a possibility as well. Here's the solution, the line. In the third option, we have the planes are all actually equations of the same plane, and so they're just all stacked on top of each other. And so this has infinitely many solutions. And in the last two, there are no solutions, and that's because maybe all of three planes are parallel, like in this one on the left, or perhaps instead the planes aren't parallel, but maybe like in this example, they're all vertical, but they don't meet in a line. And so that also has no one solution either. So each of the two planes will intersect in a line, but none of those lines are the same lines. Okay. And so here we're going to have a simple example. We have three equations and three unknowns, and I have four options here for points. I want to know what of any of these points are solutions, is a solution to the system. And so if I try option 1 here, x is 3, y is -1, and z is 2. And so if you're a solution, then you're a solution in every single equation in the system. So let's try that in the first equation. If x is 3, then I have 3 times 3, and y is -1, so I'll have 4 times -1, minus z, and does that equal 17? 9 minus 4 minus 2. That does not equal 17. So my first point is not a solution to the system because it's not even a solution to the first equation. Now let's check the second point. For the second point, x is 1, y is 3. I'm going to go ahead and multiply 4 and 3 right now and get 12, minus -2. Does that equal 17? Yes, it does. So it fits into equation 1. Now let's try equation 2. So in equation 2, I would have 5 plus, now y is 3, so minus 3, and z is -2, so it would be -4. Does that equal -2? Yes, it does. And now let's try this point in the third equation. So we're going to do 2 times 1 minus 3 times 1 plus 7 times -3. So that's -21. Does that equal -21? All right. No, it doesn't. Let me make sure I did this right. Because I'm checking. Oh, no, I'm checking the wrong point. I started checking the wrong point. Let's go back. I need to check point number 2. So does 2 times 1 plus 3 times 3, that's minus 3 times 3, minus 14. Does that equal -21? Yes, it does. And so this is a solution. This point is a solution. Okay, you've got 2 more points. I want you to try these next 2 points and let me know if these are solutions. So this is for you to do. Number 3, is point 3 a solution, and is point 4 a solution? You need to plug them in and check. Okay, so we are going to solve these from scratch, though. We're not going to just check every single point out there in the universe to see if it's a solution. We're going to systematically solve 3 equations and 3 unknowns. So our next example here is strategic. It's set up so that you can easily solve it. And the way that this works is we'll start with this bottom equation here. It's actually already solved. It tells me that z equals 2. And now I know that z equals 2. I can go to the second equation and replace z with 2, and now I can solve for y pretty quickly. So 2y would equal -8, and now y equals -4. And now finally, I'll go to the top equation with x and y and z in it, and I can replace the y with -4 and the z with 2, and I'm supposed to get 3. So 5x 34 equals 3, 5x equals -31, so x equals -31 fifths. Let me make sure I didn't make an algebra mistake. Okay, so I couldn't find a mistake. I think this is right. So now my solution is -31 fifths, comma, -4, comma, 2. And I'm all done. And so if I can get a system of equations to look like this example, well, then I know I can solve it, okay? But looking back at our first example in which we checked solutions, this equation, this system of equations doesn't look anything like that. There are there are 3 variables in all 3 of the equations. And so how do I eliminate some of those variables? Well, we're going to employ this strategy called Gaussian elimination. Gaussian elimination. Okay, so when you're in the nice form in which you can solve easily, it's called row echelon form. And we're going to do Gaussian elimination in order to get our system into row echelon form. And so here is the idea, and this is just based on me. This is the way I work every time from here on out. I use the very first top equation to eliminate the x in the very bottom equation and in the second equation. These two are actually can be done at the same time, and you can do you can eliminate the x in the second equation first and then the bottom equation next, however you want to do it. But I eliminate the x in the bottom in the second equation. So then once you get that done, the x has to be eliminated in the second equation in order for this to work. So now you're going to use the second equation and eliminate y in the bottom equation. This definitely has to be done last. Okay, it has to be done last, or else you'll undo some of the nice things you've done before. Okay, so let's solve this system of equations, and we're going to do Gaussian elimination to get this equation into row echelon form, and then after that we're going to back substitute to solve. All right, and the way that we use these equations to eliminate is we simply do linear combinations, just like we did in the last section, where for example, if I use my top equation, 2x plus 3y plus 4z equals 1, and let's say I eliminate the x, and let me start off by eliminating the x in the second equation, which is the second dot, but that can be done next. What I'm going to do is I'm going to take, I'm going to call this the second row. I'm going to take this one and I'm going to multiply this equation by -2. And I'm going to add it to equation 1. So let me write that down. I'm going to call these rows. So I'm going to take row 2 times -2. -2 times row 2, and I'm going to add row 1, and that's my new row 2. So that's the equation I'm doing, and nothing else is going to change. So this top equation is still going to be 2x plus 3y plus 4z equals 1. But now my second equation, I'm going to multiply these by -2 and add row 1. So notice what happens in the x's. When you take this one by -2, you get -2x, and then -2x plus 2x is 0. So there's a 0 here. And then this will be a 6y for the y, because I'm multiplying by -2. So 6y plus 3y is 9y. And then -6z plus 4z is -2z. And then you also have to do it on the right side of the equations too. So this is -10 plus 1 equals -9. Okay? And so what I've done is I've done the second bullet point. I did that first. I used the top equation to eliminate x in the second equation. All right. Now I'm not going to rewrite this third equation. I'm going to do that first bullet point now. I'm going to use the top equation to eliminate the x in the bottom equation. Okay, so it was pretty simple when I did it in the second one, because all I had to do was multiply the second equation by -2. In this case, there's 2 and 3. One does not divide evenly into the other. And so you're going to have to you're going to have to multiply both equations. So I'm going to multiply the top equation by 3. So 3 times row 1, or equation 1. And then I'm going to subtract 2 times row 3, and that's my new row 3. Okay? Notice I'm not actually changing row 1, right? Row 1 I've already said is the same. But for the purposes of eliminating the x in the third equation, I'm going to multiply the coefficients in row 1 by 3 in order to eliminate this x. Okay, so I'll get 6x plus 6y plus 8z equals, no, I started multiplying by 2. 6x plus 9y plus 12z equals 3. And then in the bottom, I would get negative 6x minus 4y minus 14z equals negative 8. And so now when I add those together, I eliminated the x's just like I wanted to. And then I get 5y minus 2z equals negative 5. Okay, and so you can see that I've definitely reduced the system of equations, but I'm not completely in row echelon form. Now I need to eliminate this 5y. And so in order to eliminate that 5y, I'm going to use the second equation to do it, okay? Now again, I'm not changing this first equation. I still have 2x plus 3y plus 4z equals 1. I'm actually not going to change my second equation in the end either. But I do want only a z in the third equation. Okay, again, this is not pretty because 9 and 5 are mutually prime. One does not go into the other. But I can multiply this. So what I'm going to do is I'm going to multiply 5 times the second one, and then subtract 9 times the third one, and that's my new third row, or third equation. All right, so that would give me 45y minus 10z equals negative 45. And then on the bottom, I'll have negative 45y plus 19z equals positive 45. Okay, yes. So that's going to give me 9z equals 0. 9z equals 0. And now I'm back in this nice form. I'm in row echelon form, and I can solve this easily. So if 9 times z equals 0, then that tells me that z has to equal 0. So I'll divide both sides by 9. And then if z equals 0, then y minus 2 times 0 equals negative 9. And so this tells me y equals negative 9. And now if y equals negative 9, then 2x plus 3 times negative 9 plus 0 equals 1. And so 2x minus 27 equals 1. 2x equals 28. And x is 14. And so I have the solution 14 in the x, negative 9 in the y, and 0 in the z. And that's how you solve 3 systems of equations with 3 unknowns. Okay, and so I have 2 more examples here. I'm going to attempt to do the math on this really quickly on this next example, and have you do it on your own and then check. Okay, so I know that the first thing that I want to do, the first 2 things I want to do is I want to eliminate the x in the third and second equation. And so I'm getting a new third equation and a new second equation. I'm actually not changing the first equation at all, so I can rewrite that. The second equation, I'm going to get a new equation by multiplying the first one by negative 2 and adding the second one. So that would give me y minus 2z equals 5. And then when I get a new third equation, this is a lovely thing. All I have to do is add the first equation to the third equation, and that will eliminate x. And so then if I continue adding, I get y minus 2z equals 5. Okay, and so now as you look at this, notice that the two equations I just got, the second one and this third one, they're exactly the same, right? They're exactly the same. And so when I eliminate the y in the last equation, I'm actually going to end up eliminating everybody, because I'm going to take row 2 minus row 3, and that's going to be my new row 3 or third equation, and that's going to give me 0 equals 0 in the bottom. And I have x minus 2y plus z equals negative 6, and y minus 2z equals 5. And so essentially it's like, well, I know you wrote 3 equations up there, but there's really only 2 here, because the bottom 2 are actually just are multiples of each other. They're the same exact equation. Okay, so what happens here? Well, this is the case in which you have infinitely many solutions, and it's looking to me like the solutions that are infinitely many it's a line, okay? And so what is the equation of that line? Well, in order to get this, you're going to solve in terms of another variable. And so even though I can't use this bottom equation, I'm going to start with the second equation, and I'm going to say y equals 5 plus 2z. So z, I don't know what z is. It's just itself. But whatever z is, y I know will be 5 plus 2 times z. And then I'm going to now use the top equation, x, and solve for x. So x will equal 2y plus z minus 6. But remember, y is 5 plus 2z. So x will equal 10 plus 4z plus z minus 6, or 4 plus 5z. And so what happens here is you have infinitely many solutions, and they're all of the form 4 plus 5z, comma, 5 plus 2z, comma, whatever z is. And this is a line, and it's all based on the z coordinate. And so this is your solution. This is how you have to solve this and come up with this solution. Now notice that your last example is definitely going to have infinitely many solutions, and at best it's going to be a line like this. It could be just a plane in which each of these are direct copies of each other, but let's find out. So we're going to reduce this one as well. All I can do is eliminate the x in the bottom equation. So I'm going to take negative 3 row 1 plus 2 row 2, and that's going to be my new row 2. And I'm not going to change row 1. So I still have 2x plus 5y minus 19z equals 34. But now, sometimes this helps me if I figure out the multiples. It's negative 38, no, times 3. Okay, so I've gone ahead and done the arithmetic for us. It actually, when you were multiplying the 3's in, you got some really crazy numbers, and when you multiplied the 2's in, but once you combined those, we got something really quite straightforward. And now I can't eliminate anything else, and so I'm going to solve again in terms of z. So y will equal 6 plus 5z. Z will just be z, because I can't solve for him. And then x is going to be what we get when we solve the top equation. So it's looking like 5y, or negative 5y once I subtract it over, plus 19z plus 34, all divided by 2. And so that's negative 30 minus 25z plus 19z 34 over 2. And so that is 4 minus 3z. And so my solutions are 2 minus 3z, I divided by 2 at the same step, comma, 6 plus 5z, comma, z. All right, and that's all we have.